For thousands of years, the pomegranate has been revered as a symbol of vitality, crowned with a leathery rind and filled with hundreds of ruby-red gems. But in the world of industrial agriculture, it is a logistical nightmare. You cannot simply crush a pomegranate. The thick yellow membrane holding the seeds is packed with water-soluble tannins, called punicalagins. If even a fraction of this rind is crushed, it releases an overwhelming bitterness that ruins the juice. Processing this fruit on a massive scale requires a masterful blend of optical physics, fluid dynamics, and thermodynamics. Welcome to the engineering of the crimson nectar. To process hundreds of tons of fruit an hour, the factory itself must be a perfectly engineered machine. Modern facilities utilize the forward flow philosophy. The building is strictly divided into 3 physical zones. Raw, unwashed fruit enters the red zone, passing through bubble-cleaning machines and parasitic acid sprays to strip away field debris and yeast. By the time the final juice reaches the green zone for bottling, the room is kept under positive atmospheric pressure with HEPA filtered air to prevent any airborne microbes from entering. To prevent contamination, the raw fruit and the finished nectar never cross paths. Before extraction begins, the whole fruits must pass a relentless inspection. As pomegranates move down multi-lane graders, they are rotated 360 degrees on specialized roller conveyors. Inside illuminated chambers, 32-megapixel true-color cameras capture high-resolution images from multiple angles. But it does not stop at the surface. Near-infrared spectroscopy and X-ray scanners penetrate the thick skin, analyzing the absorption spectra to estimate sugar content, known as bricks, and detect internal decay or hollow seeds. When the computer vision algorithms flag a defective fruit, perhaps one with internal core browning invisible to the naked eye, the system reacts instantly. Downstream, an array of pneumatic airguns is triggered. Within milliseconds, a precise blast of compressed air at 6 to 8 bar fires out, knocking the substandard fruit off the main conveyor to a discard chute without touching the surrounding perfect pomegranates. Now comes the most difficult phase, separating the delicate seeds, or arils, from the bitter rind. Standard crushing rollers can result in up to 20% aril breakage, ruining the yield. Instead, elite facilities use patented pneumatic and hydraulic systems, like the Juran aril system. Mechanical knives precisely score only the outer skin. Then, high-pressure jets of air and water pry the fruit open, mechanically dislodging the seeds without rupturing them. The resulting mixture of loose seeds and broken, bitter membranes is dropped into a massive cold water flotation bath. Because the densities of the components differ, physics does the sorting. The heavy, juice-filled red arils sink safely to the bottom, while the bitter yellow membranes and rind fragments float to the top, where they are skimmed away. This density separation achieves an incredibly low aril damage rate of just 2 to 3%. Even after the water bath, tiny fragments of bitter rind and remain. To achieve absolute purity, the arils are launched off a high-frequency vibrating chute into a controlled gravitational freefall. In midair, they pass through a Ventus laser sorter. Up to 16 lasers and 32 multi-spectral detectors scan the falling seeds 3,333 times per resecond, achieving a microscopic resolution of 0.3 millimeters. The lasers measure how light scatters internally, instantly distinguishing between a good red seed and a piece of red-stained bitter rind. With 100% pure arils secured, it is time to extract the nectar. To avoid crushing the hard, bitter seed hidden inside each aril, industrial facilities abandon high-pressure screw presses. Instead, they use pneumatic membrane presses. The arils enter a horizontal stainless steel cylinder fitted with a seamless, flexible membrane. This membrane inflates, gently pressing the arils against electropolish drainage channels. It replicates the gentle action of manual squeezing, capturing up to 75% of the juice while leaving the bitter inner seeds perfectly intact. The extracted raw juice is cloudy, filled with suspended pulp and fiber. It is pumped into massive continuous refiners, like the Jumbo Vortex, which uses a specialized spinning rotor to separate the remaining solids. For a perfectly clear, premium juice, the liquid is sent through an automated ultrafiltration membrane line. This strips away all suspended solids on a microscopic level, transforming the cloudy liquid into a brilliant, stable, and translucent ruby nectar. Raw pomegranate juice is biologically active. It contains enzymes like polyphenol oxidase, PPO, and peroxidase, PPOD, which rapidly react with oxygen to turn the beautiful red juice into a muddy brown. To achieve microbial safety and destroy these browning enzymes, the juice must be pasteurized. But heat is the enemy of flavor and color. Standard high-temperature short-time, HTST, processing heats the juice to 90 degrees Celsius for 30 seconds. While this kills the pathogens, it degrades the heat-sensitive anthocyanins that give the juice its red color and can even synthesize pentadecanoic acid, a compound that creates an unwanted waxy-off odor. To solve this thermal paradox, engineers are pioneering a revolutionary cold chain technique called isocaric freezing. The juice is sealed inside a rigid, constant volume chamber and cooled to negative 15 degrees Celsius. Because the volume cannot expand, the hydrostatic pressure skyrockets to 130 megapascals without any mechanical pumps. This immense pressure inactivates spoilage yeasts and pathogens without forming damaging ice crystals, preserving nearly 100% of the native antioxidants, vitamins, and that flawless crimson color. For standard liquid export, the pasteurized juice enters the aseptic filling line. Because the red anthocyanin pigments are highly susceptible to light and oxygen degradation, the juice is injected into sterilized bags or amber glass bottles that block ultraviolet light. Simultaneously, a shield of nitrogen gas is pumped into the packaging to displace all the oxygen. From the ancient forests to multi-dimensional laser sorting and precision thermodynamics, this is the reality of the modern supply chain. The crimson nectar is not just a juice. It is a masterpiece of precision engineering. If you are fascinated by the extreme scale and hidden engineering that feeds our planet, hit that subscribe button to join the Precision Yields community. We have only just scratched the surface of these billion-dollar blueprints, so stay tuned. Our next deep dive into the massive machines sustaining our future is already on the assembly line.